Well, welcome back to another fascinating review topic. We are going with exponential equations. So what is an exponential expression? Well, it's one which contains an exponent. Sounds like such a simple idea. Alright, so if you have an exponent, you are considered exponential. So if I said y equals 4 to the x, that's exponential. I have an exponent. Okay. The other thing we're going to deal with quite a bit, and you've seen it on some of our Grizzlies or just some of our tests, and some of us are getting freaked out, we're seeing this letter E. Okay, and I want to be clear that E is not a variable. E is a number. Okay, it's an irrational number, approximately 2.718. If you hit E in your calculator, it will say the same thing. And it was just named after a Swiss mathematician named by the name of Euler. A lot of people pronounce that Euler. But either way, E is a number. We want to get that straight in our head. So, e to the x and the ln of x are inverses. Now, we did not spend a ton of time talking about that idea back when we introduced this to you for the first time, so take good notes here. And we just reviewed inverses the other day. We said inverses pretty much undo each other. And the same is true for e's and ln's. For example, the ln of e to the x. Well, since the ln and e undoes each other, basically these zap out and we're left with just x. And we like to call that the zap rule, when they undo each other. Now, let me show you another example. E raised to the ln of x. Okay, so these two are going to zap out, and I'm left with x. Now, they have to be in that order to zap each other out. So again, I have to have the ln of e or e to the ln. So let's kind of box that in. I need one of those in order to apply this so-called zap rule. Let's try another one. E to the ln of 4. Now notice, there truly is no variable in here, so if you wanted, you could just type this in your calculator and verify the answer. Or you can see that this is a zap rule when I have e to the ln. So again, these are going to zap out, and you should just get 4 for an answer. And again, feel free to type that in your calculator and verify it. But there's no variable, so it's just, we can go straight to that calculator. Let me give you another example. The ln of e to the 6th. Okay, so again, notice that looks like my zap rule, the ln of e. So those can zap each other out, and I'm left with the number 6. Now, sometimes we've got somebody in our way. For example, e to the 2 ln of x. Now think about this. Do I have my little zap rule? Do I have e to the ln? Well, no, this guy's in my way. So I've got to use some log properties. If you have a number in front of a log, where did it come from? Where can you move it to? Hopefully you're saying the exponent. So I'm going to rewrite this as e to the ln of x squared. Do you recall that log property? If it's in front, it came from the exponent. Now I've got my zap, and I'm left with x squared. Now that one I couldn't type in the calculator because there's a variable up here. Let me give you another example. E to the 4 ln of 2. Now again, these are all numbers, so I could type it in, or let's apply those log properties. E, move this 4 up to the exponent, the ln of 2 to the 4th. I've got my zap rule, so now I'm left with 2 to the 4th, which of course is 16. So that should definitely be a new idea for you, and see how you feel about that before we move on. Alright, so exponential equations with like bases. So my goal is to make the two bases alike. So let me just recall, we have what's called the base, and that's always raised to the exponent. So my goal is to, again, make these bases the same. So I say to myself, alright, I want to go low. This I can leave as 5 to the 3x minus 8, and I need to rewrite my 25 as a 5. I need these two bases to be the same. What's another way to say 25? 5 squared. Okay, so basically that's the same thing as 25. And now I want to leave my exponent of 2x And once you have like bases, we literally just cancel them out. And I'm going to set my exponents equal. And of course that's 4x. And when I subtract my 3x, I should get x equals -8. And you've got it. So most of us were pretty good at getting like bases. Let me throw some ugly ones at you. Here's our first ugly one. 3 to the n plus 1 minus 5 equals 22. Now, you can't just go around getting like bases until you have two base and exponents equal to each other. Alright, so I can't have this 5 lingering around. So my first move is to add that 5 over. So I get 3 to the n plus 1 equals 27. Now I've got a base and an exponent, a base and an exponent. Of course, my exponent's just 1 here. But now I'm ready to go. So let's talk common base. I think 3 would work. Would you agree? I'm going to leave this as 3 to the n plus 1. What can you rewrite 27 as? 3 to what power is equivalent to 27? 3 cubed. So I'm going to replace that with a 3. Now that my bases are equal, they cancel out. And I'm just going to set my exponents equal. So I've got n equals 2. Alright, let's make it even uglier. Alright, now nobody likes these when we throw a fraction in there. Alright, but we just talked about exponents and negative exponents, so it shouldn't be too difficult. So I've got 1/4 to the x equals 8 to the 5x plus 2. So here's what I start thinking. Is 4 going to work? Alright, I kind of see a 4 here, so 4 juts in my mind. I could say that's 4 to the -1. Would you agree that's 1 over 4? But can 4 to any power give me an 8? Is that possible? No. Alright, so we got to go even smaller. What's another number that jumps in your head? Hopefully you're thinking 2. Okay, how can a 2 turn into a 1/4? Well, sometimes I ignore the fraction and I just kind of look at the main number. How can a 2 turn into a 4? Well, I would say that's 2 squared. And if I want the 4 to move to the bottom, that just means I have a negative exponent. And of course, 2 cubed is equal to 8. So I'm going to say I have 2 to the -2 and 2, oops, and I have an x up there, and 2 cubed, and I'm going to leave my 5x plus 2. Would you agree with that? Now, I'm not going to solve this problem because I think that's extremely simple. The hardest part is just getting the common base. Let's try another one. 1/9 to the 2x equals 27 to the x plus 2. So again, 9 might jump out at you, and that's okay. 9 to the what power is 1/9? Well, 9 to the -1 if I want it to move to the bottom. Is 9 to any power going to be equal to 27? Well, just think about it. What's 9 squared? 9 squared is already 81, so we know that's not going to work, so 9's out. What other number jumps in your head when you see a 9? Hopefully a 3. When I see 9, I think 3 squared. And again, if I want that to equal a 9th, I need to have that 3 to the -2 to get to 1/9. So I'm going to say this side is 3 to the -2, and I have to keep that exponent of 2x. 27, of course, is 3 to the 3rd, and I need to keep the quantity x plus 2. Then my bases are the same, and I'm good to set my exponents equal. Alright, when if you have unlike bases? Okay, it's just not possible to get common bases. Well, here are the rules, so let's copy them down very carefully. First and foremost, isolate. Have you noticed that's been a keyword around our math room lately? Isolate the exponential expression. Take the log or natural log of both sides and solve for the variable. Alright, example 1. 2 times 5 to the x equals 10. Now I want to stress this. When I say base to the exponent, that exponent is only sitting on the thing right beneath it. Okay, so this x is only sitting on the number 5. You cannot, and I repeat, not multiply these and raise it to the x. Box it in if you have to. This is the only thing that x is touching. So your first goal is to isolate that exponential. And that just means divide both sides by 2. So I've got 5 to the x equals 3.5. Okay, now, I'm not going to try to get a common base with a decimal, and in fact, it's not going to work. So step 2 says take the log or natural log of both sides. Watch what I do. Okay, nothing fancy. You're just going ln of 5 to the x equals ln of 3.5. Okay? Whatever you do to one side, do to the other. It's a natural log of both sides. Now apply your log properties. Okay, where is this x going to go now? X, ln 5, equals the ln of 3.5. Okay, notice I did that in 2 steps, and that's what I'm looking for in your notebooks, 2 steps. Natural log both sides, then apply the properties. Now to solve for x, I just divide both sides by the ln of 5, and I'll round to whatever it says in my calculator, or on my question. So x equals, type it in your calculator, and you're good to go. Alright, example 2. 4 times 3 to the 2x plus 1 equals 9. So self-talk first. This is exponential because I have an exponent, and that exponent is strictly sitting on the 3. Alright, so our goal is to isolate the exponential. Who are you going to move over first? And the order is important. You can't just do what you want. You got to go in order of operations here. We're first going to subtract the 1 over. So I've got 4 times 3 to the 2x equals 8. All right, I'm going to box it in again. These are attached together. You got to boot that 4 out. How are you going to move your 4 over? Well, remember it says 4 times. So common sense tells us to divide by 4. So I've got 3 to the 2x equals 2. All right, now I can't get a common base, so I'm going to natural log. This is exponential. I'm going to have an exponent up here. Again, just slap an ln in front of both sides. Do not do any log properties yet. Let's just slap an ln in front of both sides. Now you can do your log properties. That whole exponent is going to come down in front. So 2x ln of 3 equals the ln of 2. Okay, our goal is to get x by itself, so I'm first going to divide over the ln of 3. And I've got 2x equals, I don't know what that is, I'm typing in my calculator, I'm storing it into alpha A. And now to solve for x, I'm going to divide both sides by 2. And again, just whatever your calculator says, and I'm not going to work it out for you, but you get the idea, x equals whatever number that may be. Alright, let's get a nice word problem going. Matt places $1,200 in an investment account earning an annual rate of 6.5% compounded continuously. Using the formula, V equals PE to the RT, where V, and they'll tell you what these are, V is the value of the account in T years, P is the principal initially invested, E is the natural log E, and R is the rate of the interest. Determine how much money Matt will have to the nearest cent in 10 years. Okay, so again, P is the amount that you are investing. How much are we going to invest? Hopefully you're saying $1,200. E is the number E. If I say 6.5%, that's not a rate, that is a percentage. What is 6.5 as a rate? And we've done this a bunch of times now. You move the decimal 2 places. It never changes. It's the same thing every time. 2 places. So I'm going 0.065. And it says after 10 years. 10, of course, is my time. And the question is, what is its value? Now, this couldn't get any easier. Look at this. Is your variable by itself? Okay, there's no variable here. These are all numbers. You don't even need logs to solve this problem. The V is by itself. You are just going straight to your calculator and figuring out what this is. Just type that bad boy all in there and you've got your answer. If you've got that old calculator, just make sure your whole exponent's in parentheses. If you got the new calculator, you're good to go. All right, next example. The amount A in milligrams of a 10 million dose of drug remaining in the body after T hours is given by the formula A equals 10 times 0.8 to the T. Find to the nearest tenth of an hour. So we are finding the time. How long it takes for half of the drug dose to be left in the body. Well, how much of the drug dose do you have? Well, it said there was a 10 milligram dose of a drug. Therefore, you want to end up with the amount of 5. And why 5? Because it said the word half. I want half of that dose. I've got 10 times 0.8 to the T. Now again, if you can follow those few simple steps, these are very simple to solve. Just be clear that this T is attached only to the 0.8. You cannot, and I repeat, you cannot multiply those two things. That's illegal. This is attached to the T only. So your first move, hopefully you're doing it by now, is to divide both sides by 10. So I've got 1/2 equals 0.8 to the t. Okay, and I know it's exponential because, again, you have an exponent, and that rule just says take the ln of both sides. So I'm going to the ln of 1/2 equals the ln of 0.8 to the t. Okay, two-step process. Now use your log properties. The ln of 1/2 equals, bring that exponent in front, t ln of 0.8. Therefore, to get t by itself, hopefully you're just saying divide both sides by the ln of 0.8. And again, this is just some goofy number in your calculator, and I'm going to trust that we can all type that in correctly. All right, just a few more. Depreciation is the decline in value on a car, can be determined by the formula V equals C, 1 minus the rate to the time. Where V, and it'll tell you, you don't have to guess, V is the value of the car after T years, C is the original cost, R is the rate. Okay, so if a car's cost when new was $15,000 and it depreciates at a rate of 30%, and the value of the car is now $3,000, how old is the car to the nearest tenth of a year? Why don't you pause it and see if you can at least put the numbers in the right spot. All right, see if you agree with mine. My original cost, my C value, was $15,000 and it depreciated to $3,000. I did 1 minus. Again, our biggest mistake is here. This is not a percent. This is a rate. So you've got to move that decimal place 2 places to the left every time, to the time. All right, so just say to yourself again, this T, and I think you can clean up inside there. Maybe I'll go one more step. I'm going to say 3,000 equals 15,000. And instead of calling that 1.1 minus 0.3, do it in your head or type it in the calculator. That's just 0.7 to the t. And look how it looks so much nicer already. All right, you've got this one on your own. Pause it, see if we get the same thing. Hopefully you can follow my work here. Again, I just want to be clear that this exponent is attached to that 0.7 only, so I'm booting out my 15,000 by dividing. So I've got 1/5 equals this junk. Okay, exponential, I'm taking the ln of both sides, my first step, and my second step is to bring that down, so you've got my t in front there. Then I'll just divide both sides nicely by 0.7. And I get a nice, 4.512, and those of course are years. Let me just reread the question there. Just say find to the nearest tenth of a year, so I'm going with 4.5 years. Well, I think that does it for us. Hopefully you've got some great notes there, and just take your time with these, and we'll look forward to seeing you tomorrow. Have a great night.